Somewhere in the darkness between Mars and Earth, a rock the size of a skyscraper is falling toward us. Not metaphorically. Not in some distant hypothetical future that astronomers warn about in grant proposals. On April 13, 2029, a Friday the 13th, which feels almost too on the nose, an asteroid named Apophis will pass closer to Earth than the satellites currently beaming your GPS coordinates to your phone. If you're in Europe, Africa, or Western Asia that night, you'll be able to walk outside, look up, and watch it move across the sky with your naked eye. A mountain-sized boulder, close enough to see without a telescope, traveling at roughly 7.4 kilometers per second. No impact. No catastrophe. But something arguably more unsettling, proof that the universe operates on timelines we can actually perceive, and that the difference between a near miss and the end of civilization can come down to a corridor of space a few hundred kilometers wide. This is the story of Apophis. And it's worth understanding in full, because what makes this asteroid remarkable isn't just how close it's coming, it's everything that happened before it got here, and everything that changes after it passes. In June of 2004, astronomers Roy Tucker, David Tholen, and Fabrizio Bonodi were conducting a survey at Kitt Peak National Observatory in Arizona. They were doing what optical astronomers do during asteroid surveys, systematically photographing strips of sky and comparing frames to find anything that moved. Most objects they found were unremarkable. This one wasn't. The object they designated 2004 MN4 appeared on their images as a faint smear of light, but the mathematics of its trajectory was immediately alarming. They submitted their observations to the Minor Planet Center and waited for others to collect more data. By December 2004, the scientific community was in a quiet state of alarm. Additional observations had refined the orbit, and what astronomers were seeing was unprecedented in the modern era of asteroid tracking. The probability that this object would strike Earth in April 2029 climbed to 2.7%. That doesn't sound like much. But in asteroid terms, it was the highest probability of impact ever recorded for an object of that size. It briefly hit a 4 on the Torino Impact Hazard Scale, a scale designed to communicate collision risk to the public, where 0 means no concern and 10 means certain global catastrophe. A 4 had never been assigned to anything before. Scientists started running numbers on what a collision would actually mean. Apophis is roughly 340 meters across. Think of the Eiffel Tower lying on its side, then imagine two of them end to end, and wrap that in solid rock. An object that size, entering the atmosphere at interplanetary velocity, doesn't just make a crater. It releases energy equivalent to roughly 1,000 megatons of TNT, about 65,000 times the yield of the bomb dropped on Hiroshima. If it struck land, it would obliterate everything within a radius of several hundred kilometers and send debris and shockwaves far beyond that. If it struck ocean, which covers 70% of Earth, it would generate tsunamis capable of devastating coastlines thousands of kilometers away. It wouldn't end civilization the way a truly large impactor might. The kind that wiped out the dinosaurs was 10 kilometers across, roughly 30 times bigger, but it would be, without any exaggeration, the worst natural disaster in recorded human history. For a brief few weeks in late December 2004 and early January 2005, humanity technically had a date with potential catastrophe circled on the calendar. Then more data came in. Archived telescope images from earlier in 2004 were recovered and incorporated into the orbital calculation. The probability dropped. Then dropped again. By the end of January 2005, it was clear Apophis would not hit Earth in 2029. Scientists breathed. The news cycle moved on. Most people never knew this had happened at all. But the story wasn't over. Because when astronomers modeled the 2029 flyby with the updated orbital data, they found something that kept the asteroid interesting in a different, more subtle way. The 2029 pass would be extraordinarily close, closer than geostationary orbit, which sits at about 35,786 kilometers above Earth's surface. Apophis would slide by at around 31,000 kilometers. And at that distance, Earth's gravity would do something significant. It would bend Apophis's path, reshape its orbit, send it off on a new trajectory. The question was, which trajectory? This is where the concept of a gravitational keyhole becomes genuinely unsettling. A keyhole, in orbital mechanics, is a specific narrow region of space that an asteroid must pass through during a close flyby in order for Earth's gravity to redirect it onto a collision course in some future pass. For Apophis in 2029, that keyhole was calculated to be roughly 600 meters wide, smaller than the asteroid itself. If Apophis threaded that needle during its 2029 flyby, Earth's gravity would act like a slingshot, bending its path just enough to set it on a collision course for April 13, 2036. 7 years later, almost to the day. The probability of that happening was eventually calculated to be about 1 in 45,000 for the 2036 scenario. Small. But not zero. And the asymmetry of the stakes made that small number feel heavier than it looked. If astronomers were wrong, if Apophis passed through the keyhole, the world would have 7 years to mount what would be the most consequential engineering project in the history of the species. Deflect an asteroid, or watch it hit. In March 2021, those concerns were finally and permanently put to rest. Using radar observations from Goldstone Solar System radar in California and Arecibo Observatory in Puerto Rico, one of its last major contributions before its catastrophic collapse, scientists obtained precise enough measurements of Apophis's position and velocity to rule out any Earth impact for at least the next 100 years. The keyhole scenario was dead. The 2036 threat was gone. And suddenly, what had been a source of anxiety became something else entirely, the scientific opportunity of a lifetime. Because Apophis is still coming. The close approach still happens on April 13, 2029. And now, instead of bracing for disaster, the planetary science community is preparing to watch and to send a visitor. NASA's OSIRIS-RX spacecraft, which spent years at the asteroid Bennu collecting samples and returned them to Earth in 2023, has been retasked. Renamed OSIRIS-APEX for Apophis Explorer, it's currently on course to rendezvous with Apophis shortly after the 2029 flyby. The mission will allow scientists to study the asteroid up close, watch how Earth's gravity affects its surface, and investigate whether the tidal forces of the flyby cause any visible changes, landslides, structural shifts, the exposure of fresh material from beneath the surface. This kind of intimate interaction between a large body's gravity and a passing asteroid has never been observed before in real time. Other space agencies are circling the opportunity. The European Space Agency, Japan's JAXA, and several private groups have expressed interest in missions of their own. In the world of planetary science, April 2029 has become something like a scheduled solar eclipse, a predictable celestial event worth building entire careers around. What makes Apophis so scientifically valuable isn't just its size or its proximity. It's the timing, and what the flyby will do to the asteroid itself. Apophis belongs to a class of asteroids called S-type, meaning it's composed primarily of silicate rock and iron-nickel metal, similar to the composition of stony meteorites that fall to Earth. Its surface has been shaped over billions of years in the asteroid belt and in near-Earth space, bombarded by micrometeorites, heated and cooled by the sun, tumbling slowly through the void. During the 2029 flyby, Earth's tidal forces may shake loose surface material that hasn't been disturbed in geological timescales. Scientists will effectively get to watch the asteroid react in real time, which is something that has never been possible in any previous close encounter. There's also a more fundamental question that Apophis helps illuminate. We live in a solar system that is not static. It is not a clockwork mechanism of perfectly predictable orbits. Small forces, the pressure of sunlight, the gravitational nudges of planets, the Yarkovsky effect in which an asteroid slowly drifts due to the tiny force of asymmetric thermal radiation, accumulate over decades and centuries, making long-range predictions difficult. The fact that we couldn't definitively rule out an Apophis impact until 2021, even though the 2029 flyby was already known in 2004, is a direct illustration of how sensitive these calculations are. We needed 17 years of increasingly precise observations to close the case. That's the counterintuitive part. We tend to think of space as vast and empty, and we tend to think of planetary orbits as stable and known. But the region of space Apophis inhabits, crossing Earth's orbit twice on every trip around the Sun, is a dynamic, chaotic environment where small uncertainties compound over time. Apophis is one of roughly 2,000 potentially hazardous asteroids currently catalogued. These are objects large enough and on trajectories close enough to be considered in ongoing monitoring programs. The vast majority of them, like Apophis, will never strike Earth. But the monitoring programs exist for a reason, because the difference between a near miss and a catastrophe can, in some cases, be measured in meters. The 2029 flyby will be visible to the naked eye for millions of people. For a few hours, Apophis will move visibly across the sky not as a stationary point of light like a star, but as something perceptibly in motion. People in parts of Europe will see it pass through the constellation Cancer. In the Middle East, it will be visible against a different patch of sky. The apparent speed of its movement will be detectable without any equipment. At its closest, it will be moving across the sky at about half a degree per minute, roughly equivalent to watching the minute hand of a clock if that clock were the size of the full moon. Not a blur. Not a streak. But unmistakably moving, unmistakably real. Apophis was named after the Egyptian god of chaos and darkness Apep, the serpent that was said to threaten to swallow the sun. The astronomers who named it were being a little theatrical, but they weren't entirely wrong to reach for that kind of imagery. For a few weeks in late 2004, this rock in the dark was genuinely threatening. It occupied a rare and uncomfortable space, large enough to cause a regional or continental catastrophe, close enough to track with precision, and uncertain enough in its trajectory to demand serious attention. The fact that it turned out to be safe doesn't erase that. It confirms something more important, that our monitoring systems work, that our models improve as data improves, and that the difference between panic and preparedness is precisely the kind of patient, unglamorous observational work that those astronomers at Kitt Peak were doing when they first spotted that faint smear of light in 2004. On the night of April 13, 2029, Apophis will be closer to Earth than the communications satellites relaying this video to your device. It will pass silently, at tens of thousands of kilometers per hour, close enough that if anyone were standing on its surface, they would be able to see Earth's continents with the naked eye. And then it will continue on its way, reshaped slightly by Earth's gravity, carrying a new orbit into a future that our models say is safe, but which we will continue watching, because that is what we now know how to do. The 65-million-year-old crater that marks the end of the dinosaurs is a record of a day when no one was watching. April 13, 2029 will be different. Every telescope, every radar dish, every spacecraft we can point in that direction will be aimed at Apophis as it passes. That transition, from a species that had no idea what was coming, to one that tracks every sizable rock in the inner solar system and can watch them as they slide past us, happened within living memory.